Now you draw the electron configurations for the following atoms using noble gas notation. Chlorine, we look up and we see it's element 17. Neon is the nearest preceding noble gas, so we'd start out with brackets around neon, and we would finish with the next 7 electrons. So we finished the second period, we're at the third, so we'd have 3s2, 3p5 to give us the 7 electrons that are highest in energy. Iron has 26 electrons. Its preceding noble gas is argon. So those first 18 electrons are represented with the brackets around Ar. And then we have 8 more electrons, which would be 4s2, 3d6. Cadmium has 48 electrons, and its nearest noble gas that precedes it is krypton. So its noble gas configuration would be krypton Kr in brackets for the inner core electrons, followed by 5s2, 4d10, and that 10th electron is our last electron. Tungsten has 74 electrons, and its nearest noble gas that precedes it is xenon. So its noble gas notation would be xenon, Xe, in brackets, followed by 6s2, 4f14, and then 5d4 for those last 4 electrons. Now, as we're looking at electrons, and the whole point of learning about electrons is to understand how elements combine with other elements to form compounds, why reactions occur the way they do. And really what we're interested in is what's called valence shell electrons. Those are the ones that are involved in bonding. They are the electrons in the outermost principal energy level. They're usually found in the s or the s and p orbitals. Normally, the maximum number of valence electrons would be 8. So if I were to ask you how many valence electrons are in carbon, you would have to look at the fact that its highest energy level is the second energy level, and it is 2s2, 2p2. So that means 2 electrons in the s sublevel and 2 in the p sublevel for a total of 4 valence electrons for carbon. Magnesium has 12 electrons overall, but those aren't all valence electrons. We have an inner core from neon, followed by 3s2. So at the highest energy level, the third energy level, it has 2 valence electrons at that s sublevel. So it has 2 valence electrons overall. Bromine has 35 electrons overall. Its noble gas configuration is argon, then 4s2, 3d10, 4p5. Now remember, valence electrons are the s and p electrons of the highest energy level, so we're not going to use those 3d electrons. They don't count as part of the valence level because they're still part of the third energy level, even though they overlap here, the 4s. So we have 2 in the 4s, and we have 5 in the 4p, for a total of 7 valence electrons for bromine. Radon has 86 electrons overall, and it's at the 6th energy level. And notice it's down there at the end, so it ends with 6s2, 4f14, 5d10, 6p6. So at the 6th energy level, the highest energy level involved, we have the 6s2 and the 6p6 for a total of 8 valence electrons. Now, this brings us to the idea of an octet. Remember that if you have s and p orbitals at the highest energy level, then that's 2 electrons at the s and 6 to fill the p for a total of 8 electrons at the highest energy level. So that's called an octet of electrons, and it's a very stable arrangement. There are a couple of elements, hydrogen and helium. It's impossible for those 2 elements to have electrons in a p sublevel because they only have electrons at the first energy level. And if you recall from quantum theory, the first energy level only has 1 sublevel, the s sublevel. It would be full with 2 only, not 8. So extra stability comes around from having that full sublevel, but although an octet is very stable, and it's more stable than an incomplete octet, there is also some extra stability in having a half-full sublevel. If it's an S sublevel, it would be half full with only one electron instead of two. And a P sublevel, since it can contain a maximum of 6, it would be half full with only 3 electrons. And according to Hund's rule, you'd have one up in each of those P's, and that's a fairly stable arrangement. Not as stable as being totally full, mind you, but it is more stable than any other arrangement being incomplete, with less than 3 for the P sublevel, or more than 3 but less than 6. So this results in some electron configurations not exactly working out the way that you expect. For example, copper has 29 electrons. Its expected noble gas configuration would be argon in brackets for its inner core, 4s2, 3d9. Now, that looks great. It follows all of the rules, but it doesn't take into account this extra stability from full and half-full sublevels. Notice that that D sublevel is only one away from being full, and the S sublevel is one away from being half full. We could have extra stability if we had a half full S sublevel and a completely full D sublevel, because then we'd have one of each. We'd have a full and a half full instead of just a single sublevel that's full. So its electron configuration actually works out to be argon 4s1, 3d10, by moving one electron up from the 4s sublevel that was full, promoting it to the 3d sublevel that was only one away from being full. What we end up with is a 4s sublevel that is half full and a 3d sublevel that is completely full. So we have both a half full and completely full, giving extra stability. Now let's try chromium. See if you can predict what the electron configuration would be. What's expected would be the noble gas inner core that looks like argon's electron configuration, followed by 4s2, 3d4. So ask yourself, are either of those energy levels near to being half full or completely full? If you look carefully, you see that the S sublevel is full, but the D sublevel is only one away from being half full. So by promoting one electron from the S sublevel up to that D sublevel, we'll get two half-full sublevels. The 4S will be half full with 1, and the 3D will be half full with 5. So this configuration could become more stable by promoting that electron from the 4S sublevel to the 3D sublevel, giving you two half-full sublevels. Now those inner shell electrons are electrons that are not in the highest principal energy level. They also have energies that are less than the principal energy level. All electrons, but valence electrons, are considered your inner shell electrons. And these are the ones that can be represented by putting that nearest noble gas in brackets, like neon in brackets. So the number of the inner shell electrons is the total electrons minus your valence electrons. So if I asked you how many inner shell electrons are there in sulfur, you would look up sulfur and see that it would be neon in brackets, 3s2, 3p4. So that looks like there's 6 valence electrons from the S and the P sublevels of that third energy level. So when I take 6 away from the total of 16 electrons, that tells me that there are 10 inner shell electrons. Or, since I'd already figured out that neon was the nearest noble gas, those 10 electrons are the inner shell electrons, the 10 that neon possesses and would be part of the inner core that's like neon. We'll do these other two examples in class. Now let's look at unpaired electrons. What is an unpaired electron? Well, it's when only one electron is in an orbital that could hold 2 but only currently holds 1. Now, you have to remember Hund's rule if you're going to figure out how many unpaired electrons there will be. You have to apply Hund's rule as you're putting electrons in, or this will not work out for you. How many unpaired electrons are in nitrogen? So we look at nitrogen, and we know its highest electrons would be 2s2, 2p3. So what we're really interested in is that final sublevel, the 2p sublevel. As a p sublevel, it has 3 orbitals. So I would draw 2px, 2py, and 2pz, and I would place my 3 electrons in there. When I do that, what I get is 3 orbitals with 1 electron in each one pointing upward as an upward arrow. So that means I have 3 unpaired electrons for nitrogen. For oxygen, we have 8 electrons overall, but 2 of those are at the lower sublevel. At the second energy level, we have 2s2, 2p4. Once again, I'm interested in that final notation, 2p4. So when I draw my 2p sublevel, px, py, and pz, I have 1 up in each, and then that 4th electron is down in the px. So what I end up with then is 2 unpaired electrons, 1 in the py and 1 in the pz. So there are 2 unpaired electrons for oxygen. Sulfur is similar in nature. It has a 3s2, 3p4 for its highest energy level electrons. And so it also has 4 electrons in the p sublevel, so it would have 2 that are unpaired, just like oxygen does. Sodium has 11 electrons overall, with its highest energy electron at the 3s sublevel, 3s1. So there's only a single orbital there, so I draw my 3s, I draw my 1 up arrow, which means I have 1 unpaired electron for sodium. And finally, chlorine has 17 electrons overall. Its highest energy level goes 3s2, 3p5. That highest energy sublevel, that p sublevel, has 5 electrons in it. So I draw px, py, pz. I draw an up arrow in each of those 3, followed by a down arrow in both px and py, which leaves pz as my only orbital that has 1 unpaired electron, which gives me 1 unpaired electron for chlorine. Thus ends section 5.2, which gave you a lot to think about. I hope you found it to be helpful.